Welcome again to my YouTube channel, Tech Guru Gautam Prasad. This video is continuation of the third video, uh, part three, basically, uh, in which we had discussed up to this series LC circuit. Now we are going to discuss parallel uh, AC circuits or LC circuit. Uh, Parallel AC circuits includes parallel RC circuit, parallel RL circuit, and then parallel LC circuit. Uh, LC circuit is the part of the parallel AC circuits. So passive components in the AC circuits can also be connected together in parallel combination in the form of RC, LC, and RL. So let's begin with parallel RC circuit. So here you can see this resistance and capacitance are connected in parallel, and they have been put across this AC source Vs, and this Vs is causing a current Is. So let's try to analyze this situation. Now this Is is branching into IR and IC. So here this current Is is dividing into two parts, basically IR and IC. IC is traveling towards the capacitor and IR is traveling towards the resistance. Now, what is the value of IR and IC? IR will be equal to Vs, that is the voltage across resistance, divided by R. IR equal to source voltage divided by the value of resistance. IC is equal to mm, source voltage divided by its reactance, and Is is not the algebraic sum again of the two currents IR and IC, but it's a vector sum, and the magnitude of Is is equal to Is, that is source current, is equal to the square root of the square of IR, uh, a square root of the square of IR, and plus IC square. So these two currents, IR and IC, have been squared and they have been summed, and then the square root is found to calculate the value of the source current. Now, what is the value of the phi, which is the angle with which your current is going to lag or lead? So, current will have a lead angle of tan inverse uh, IC upon IR. So, this is the value of the current. Okay. So, basically, the current is going to lead. IC is a leading current. IR will be the current in the same phase, but the resultant current IS is going to lead or lag. So basically it is leading current between 0 to 90 degree. So IS is going to lead VS. Now Y is a value that is called admittance, and that's inverse of this value of impedance. So Y equal to 1 upon Z, and that is equal to a square root of G square and B square. Now these two terminologies are uh, inverse of XC and XL. So G is uh, G is the inverse of resistance, that is called capacitance. Inverse of resistance, that is called conductance, not capacitance. And BC is the value of inverse of XC, and that is called susceptance, inductive capacitive susceptance. Okay, and Vs, that is source voltage, will be equal to the voltage across the resistor and voltage across the capacitor. That's it. Now let's proceed to parallel RC circuit. Here you can see resistance and this uh, inductor have been put in parallel across this source voltage. Now IS is again branching into two parts, IR and IL. But IS is not going to be again the sum of algebraic sum of these two currents, IR and IL. Again, here also this will be vector sum. So the magnitude of IS will be equal to square root of IR square plus IL square. And the current through the resistor will be equal to Vs, that is source voltage, and divided by R. So Vs upon R is the IR. IL will be equal to Vs upon XL. And the lagging current will be, the angle of lag will be equal to tan inverse IL upon IR. Again, Y, that is admittance, is equal to the inverse of impedance is equal to a square root of G square plus JB square, that is conductance square plus inductive susceptance square. So this is equal to Vs equal to Vr equal to Vl. So all these three voltages, Vs, Vr and Vl, all these three voltages will be equal. Taking forward to parallel LC circuit. Now in this circuit, uh, inductor and capacitor, these two passive components have been put together in parallel and they have been connected across the voltage Vs. Now again in this situation, Is is branching into two parts, IL and IC. Now BL is equal to 1 upon XL, BC is equal to 1 upon XC. BL is uh, inductive susceptance, as I told you, and BC is capacitive susceptance. And they both are equal to the inverse of their own inductive reactance and capacitive reactance. All right. So admittance is again the inverse of impedance, and that is equal to BL plus BC. A resonant frequency, in this case, this is also called a tank circuit together, these two L and C. If you adjust the value of frequency in this case to such a value where these two values XL and XC become equal, then that condition is called, the condition of resonance. So that frequency is basically given by Fr equal to 1 upon 2 pi square root of LC. And at Fr, XL becomes equal to XC. These two values become equal. So basically, uh, they basically when they become equal, the case of resonance occurs because the current goes high in this situation as well. So here in this situation, IL and IC are equal. Vs is equal to VL and that is equal to VC in this situation. All these three voltages, voltage across the inductor, voltage across the capacitor, is equal to the voltage of source, that is source voltage. Now, having completed these three configurations, parallel configurations, RL, RC, and LC circuits, now we are coming to one of the most important part of the circuit, that is called RLC series circuit. So here this R resistor, L inductor and C capacitor, they have been connected in series and they have been connected to the source Vs. So what happens actually in this case? So what will be the value of impedance? what will be the angle of lead or lag in this case, whether the current will lead or lag, that's the question arises. So, what will be the behavior of the current in this circuit? We are going to explore that. So, basically, if capacitor dominates, uh, then this current Is becomes leading. If inductor dominates in this circuit, this Is becomes lagging. So it all depends on the values of inductor or the capacitor in the circuit. What is going to be the behavior of Is? Is is going to lead Vs or lag Vs. Basically, is decided by the values of L or C. As we have seen, resistor does not mm, have its own, prejudice as far as current is concerned. Uh, that means it does not play any role in leading or lagging the current. Basically, the voltage and the current are in the same phase if the resistor is there only. So here also L or C, the value of L and C plays the more role in deciding whether what will be the behavior of Is uh, in this circuit. So the value of Z will be equal to a square root of R, square root of R square plus XL minus XC to the whole square, or XC minus XL to the whole square. That depends which one is having the greater value. Now Z equal to angle phi, and which is equal to R plus JX. X is the difference of these two. Here X is nothing but the value of XL minus XC or XC minus XL. Okay. Now what will be the voltage, net voltage Vs? So Vs is again the vector sum of uh, these three voltages. So vector sum of these two voltages L and C is the difference basically. So VL and VC uh, are opposite in nature. One is, if you consider one to be positive, the other will be negative. So uh, the difference of these two values and squared. So it is basically Vs is equal to a square root of the voltage across the resistor square plus the difference of the voltages in inductor and capacitor squared. So Is equal to, Is is the current, source current. That is the same current in all these three passive elements. The same current Is is flowing through R, L, and C. So there is no branching as it is a series circuit. So Is is equal to Vs, that is source voltage, divided by uh, impedance, and Vs divided by impedance. If you substitute the value of impedance, it is equal to the square root of R square plus XL minus XC to the whole square. So phi, that is the angle of lead or lag, is equal to tan inverse XL minus XC upon R. XL minus XC upon R. And the current in all these three elements are equal. Is equal to IR equal to IL equal to IC. So that is it. Now let's discuss this parallel RLC circuit. This is also an interesting one. So if you have connected them in parallel, R, L, and C all parallel across the voltage source, then it is called parallel connection. So Is here, the source current is branching into three parts: IR, IL, and IC. So this is a little complex, but yet it can be analyzed. So here, for convenience, G is equal to, that is conductance is the inverse of resistance, and inductive susceptance is the inverse of inductive reactance, and uh, uh, capacitive susceptance is inverse of capacitive reactance, and your admittance of the circuit is inverse of impedance, and which is equal to this is what I was saying. In order to make it easier, the calculation and understanding to be easier, we have taken the inverse here. That basically explains better. So this is your admittance is equal to a square root of g square plus bl minus bc to the whole square. So taking the inverse basically makes our understanding easier. And we have also defined the mm, respective terminologies, like what is uh, reciprocal of resistance is called, what is inverse of resistance is called. Okay, and is will be equal to a square root of ir square plus il minus ic to the whole square. Unlike in the series circuit, which was vr square plus vl minus vc whole square, this was equal to vs. So in the series circuit, we were calculating vs, and here we are calculating is. That's the difference. You should mind it. This, this must be remembered. Now here also resonance can happen, and for the resonance to happen, you have to have a particular frequency, and that frequency is equal to 1 upon 2 pi root square root of LC, right? And in this case, Vs, Vr, Vl, and Vc all are equal because the source voltage is appearing basically across all these three elements, right? So hopefully you have understood all these parts, and I'm going to discuss rest of the part in the next video. This is fourth part. In the fifth part, we will discuss rest of the things. Thank you very much. Stay happy, stay tuned, and don't forget to like, subscribe, and comment. Your comments are basically valuable for me. That gives me insight how this video can be made better. Thank you so much.